welcome to lecture number 18. So, we have been discussing about the orbital parameters. So, in that connection we will solve one more problem, and see the problem is defined here. Basically, it is a satellite launching problem, also it is a trajectory change problem, which we are going to do little later, but because this is a very simple one. So, we can include it with the our satellite orbit determination problem. So, a satellite is launched with the following conditions. Already you know this quantity we have discussed so many times. This is given phi 0, this is the flight path angle, this is given, and the initial position of the satellite, not in terms of the vector, but in terms of just a scalar quantity. So, this is non-dimensional quantity. R is the here the radius of the earth, as it is shown here. R is the radius of the earth, phi 0 is the flight path angle. Okay. So, what is the question? Determine the orbital parameters E, A by R. So, eccentricity and the semi major axis is to be determined, and establish the initial position with respect to the perigee. That means, with respect to the perigee initial position, how do we determine? This will be determined in terms of theta, the true anomaly. So, this we need to work out, and then if we assume that the satellite continues along this orbit. So, wherever the satellite has been launched, okay. So, from there it continues till true anomaly. Once the true anomaly reaches a value of 150 degree, at that time the orbit is to be changed to A by R. Now, the semi major axis is to be changed without changing the abscess line, means the periapsis line you do not have to change, where the perigee location is there, from focus to the perigee location. So, that line has not to be changed, that should not rotate, it will remain the same. So, determine the required increment in the velocity and its direction. So, how much velocity increment will be required? This is a trajectory transfer problem basically, but this part, because other parts it is related to orbit determination. So, we are doing it here in this place, and this is a very simple problem, and it is a direction. Okay, so, we start with the problem. This is given 1.40 and phi 0 is given, which is a flight path angle equal to 20 degree, and r 0 by r, this is given to 2.0. Okay. So, we have to get the value of what is A by R and what is the eccentricity. These two things we have to determine. We start with h square equal to mu times L. So, this implies and we know if the orbit looks like this, satellite has been launched and like this, and this may be the injection point. So, this is the velocity vector, and from here to here this is the r vector, and this is E r cap, this is the velocity vector. So, this angle is alpha, and here this angle is phi 0, okay, and this becomes your r 0. So, if this is the periapsis line or perigee line, so we have here this angle we have referred to as, in this case we will write as theta 0, means the initial true anomaly initial true anomaly. So, H, as we know, this is r cross V magnitude square divided by mu, and in this case the mu will be the value for the earth, which is g times m, g times m earth. This is velocity. Okay. So, this will be r times V sin alpha square divided by mu. Okay. And because alpha is not given, but phi is given. So, therefore, we can write this in terms of, and here we will make it r 0 v 0. So, r 0 v 0 sin alpha square divided by mu. So, r square v square 0 divided by mu, and what is the value for sin alpha? So, this will be sin 90 degree minus phi 0. So, this gets reduced to cos phi 0 divided by mu. So, this is the value of L. Now, r 0 v 0 square is given divided by mu. So, we write this as r 0 v 0 square divided by mu times cos phi 0 times r 0 is times r 0. Okay. So, we insert the value, this becomes 1.4 and cos 20 degree, and r 0 is 2 times r. So, that value we can insert here. Okay. So, for the time being, let us keep it like this, L equal to 1.4 cos 20 times r 0. We know the value of the r is around, it depends on the, if you want to take it simply, this is 6,400 kilometers, otherwise a more accurate value is 6,374 kilometers. Okay, so, this gets reduced to 1.2362311 r 0. Okay, done on some simple calculator. I am not truncating or trying to present a systematic value, because here if you truncate it, we do a lot of error in the estimate. So, on the computer the things are done in double precision, so that you maintain the accuracy of your result. So, this is one. R 0 V 0 square divided by mu is a given. So, this is R 0 divided by 0.6. So, basically 10 by 6 R 0 equal to 5 by 3 R 0. So, A equal to 5 by 3 R 0. So, already we have written the expression for the L. We utilize it to find out 8 times 1 minus E square, this quantity is L. So, from here the L we have written, the expression for A we have written, therefore, 1 minus E square equal to L by A, and from the previous one L equal to 1.236 like this. 1.2362311 r 0 and A we have written as 5 by 3 r 0. So, r 0 cancels out. So, we do not have to again put the value of the r 0 and work it out. So, here in this cancels out. So, this is 3 times 1.2362311 divided by 5. Okay, so, this is the value here and E a square this equal to 1 minus 0.741738 and therefore, E becomes 86 under root and this value will be 0.580 0.5508 1941. So, E equal to 0.5081941 and remember the A we have written as 5 by 3 times r 0. Okay. Though we have not written it explicitly. So, if you put r 0 is given to be 2 times r. So, this is 2 times r and if we insert the value say 5 by 3 times 2 times 6374. So, in that case if we use this value of 6400. So, depending on the value used here. So, we can write this as 3 duni 3 this is 2 1 and so, this becomes around 21246.7 kilometers. Why? Because this is 5 by 3 times 2. So, this is 10 by 3 which is nothing but 3.333 like this. Now, this times 6374. So, that will exceed your value of 20,000. So, this is what we are getting. Okay, so, this is our result number 1 2, this is 3, we can write this as 4. Okay, the question other things were determine A by R. Okay, so, the question was also finding A by r, how much this will be. So, we have A by r, already this A by r 0 we have written. So, A by r 0 we have got as 5 by 3 and r 0 by r is given to be 2. So, this is 10 by 3. So, this is 3.333. So, A by r. So, this is was one part in the question. This is fourth. And then okay. What else is remaining? Determine the orbit parameters E, A, R and establish the initial position with respect to perigee. So, we have to determine theta also. So, we proceed in the usual way, L by 1 plus E cos theta, this equal to r 0 and this is theta 0. So, here what is required, that theta 0 equal to what? This is the initial position in terms of true anomaly, terms of true anomaly. This is required. So, cos theta we have to determine, theta 0 we have to determine. So, we start with writing 1 by r 0 minus 1 e cos theta, L by r 0 equal to 1 plus e cos theta. So, this is and cos theta 0, therefore, this is 1 by e times L by r 0 minus 1. Already we have determined all these quantities. Okay. So, here in this case 0.5081941 L by r 0 we have already determined here. L equal to 1.23. So, L by r 0 from here becomes 1.23623, 1.2362311 minus 1. This is the L by r 0. And once we solve this, so we get here cos theta 0, this equal to 0.2362311. So, as earlier also I have mentioned that this alone is not sufficient to determine the value of theta 0. So, we also require sin theta 0, so that we can resolve the problem. Now, therefore, we utilize the relationship. This is the way you can work out in the exam, the way I am doing. So, write it L by r equal to 1 plus e cos theta, everything you need not remember, L by r square r dot, this equal to minus e sin theta times theta dot and minus e sin theta, and theta dot is nothing but h by r square. Okay. So, there minus minus sign, this drops out, this will and this will, they will cancel out, this r square and r square, this will cancel out, and then we are left with L times r dot equal to e sin theta times h, and e sin theta, this equal to L r dot divided by h, e also will remove from this place. Now, r dot is the radial component of the velocity vector. So, if we go back here in this direction. So, this is r dot here in this direction. So, this will be V 0 cos alpha. Okay. So, r dot is V 0 cos alpha. So, L times r 0 V 0 L times V 0 cos alpha divided by E times H L times V 0. Now, alpha is 90 minus phi. So, this is cos 90 minus phi is 20 degree is given E times H. So, therefore, this gets reduced to L V 0 cos phi becomes sin phi, cos 90 minus phi, that becomes sin phi divided by E times H. So, we have sin theta equal to, here we will write it sin theta 0, because we are looking for the initial value. So, L V 0 divided by E H sin phi. So, we need to insert the values to get the solution. Now, also we remember that here this L is written in terms of see the mu times L, this is written as H square. Okay. So, we need to eliminate some of the things from this place. So, if we eliminate L by H, if we write it like this L by H, so you can see that this will be H by mu. So, this can be rewritten as L by H equal to L by H equal to H by mu V 0 sin phi and divided by E. Okay. Now, H already we have written as r cross V magnitude, this is r 0 V 0 sin alpha, and this we have written as r 0 V 0 sin alpha is nothing but sin 90 minus phi equal to cos phi. So, this is here becomes cos phi. So, this is your H. So, therefore, if we insert this H here, so r 0 V 0 cos phi sin phi divided by mu e, and V 0 is already there. So, 1 V 0 square becomes, now this is in a format where you can work it out, sin phi cos phi divided by E. So, all the values are now known, r 0 V 0 square divided by mu, this is given to be 1.4 sin 20 degree times cos 20 degree and divided by E, which we have already determined. E value we have written to be 0.5081941. So, this is sin theta 0. So, more compactly, one more step we can write as 0.7 sin 40 degree divided by 0.5081941 into 0.8853926. So, this is sin theta 0. 0.8853926. And cos theta 0 we have got as 0.2362 311. See, in the actual calculation, even a small angular difference, though for our purpose it is so much of number of digits, it is not required, but you remember that a very, if we are looking for 6400 kilometers distance, okay, 6400 kilometer difference, and you do a mistake of say 0.1 degree in evaluation. So, 0.1 degree, this will be around 0.1 pi by 180, means it is approximately 3.14 into 0.1 divided by 180. So, 3.14 divided by 18, this much of radians. So, it is converted into radian. And if you are multiplying it by 6400 kilometers, you have committed a mistake. This is just the radius of Earth. Let us take double of that, where the initially the satellite is located. So, this is the error done. So, see what will be the corresponding value. This is r, and if this is theta in radians, so this distance becomes r times theta. So, this is the principle we are using. So, this is your theta in terms of radians. Sorry, here this will be 0.314. This is once we okay, this is fine 3.14, because here oh sorry, here this will be 1800. 3.14 divided by 1800. So, if we cancel out this part, okay, so this gets reduced to 128 into 3.14 divided by 18 kilometers. So, 0.1 degree of error. Let us check once more. This is 0.1 degree. So, 0.1 degree times pi by 180 radians, it is converted, and 1 radian is around 3.1, pi is 3.14, 0.1 here divided by 180. So, we convert it 1 by 10. So, this is 1800, 3.14 by 1800, okay. And this multiplied by at the distance we were looking for. So, 2 times r 0, this is 2 times r 0 equal to. So, at distance how much error we will be doing. So, 128 times 3.14 divided by 18, and if we approximate this by 7, let us say this is approximately 7. So, this is 21.98 kilometers. So, this much of difference, if you do an error of 0.1 degree in measurement. So, this much of error you will be committing in positioning the satellite, okay, and this is very large error, very large error. Okay. And suppose then you are dealing with an interplanetary satellite, like your satellite is going to Mars and other position. So, you require very accurate value in these positions. So, therefore, while dealing with doing the orbit determination for interplanetary satellite or even for the Earth satellite, where the precision is required, the angles are not involved, because the small error in angle, it will result in large error in the position of the satellite. So, 0.1 degree results in 21 kilometer. If you make it 0.01 degree, so this will be 2.198 kilometer. Still, it is a large. Okay. So, if you are looking for some precision maneuvers like the docking and other things, so these things will not work simply. Okay. So, if this is one learning that we need very precise value in terms of angles even, and therefore, the angles are quite often avoided in the satellite orbit determination problem, because this creates a lot of problems. Okay. Now, based on these two, we need to find out the theta. So, we can see that both of them are positive, this and this both are positive. So, that means it is lying in the first quadrant as we have discussed in the last lecture, and then this turns out to be 62.2999858 degree. So, if you approximate, this is 62.29, almost this is 62 point, or you better we can write, if we approximate 2.62.3, and we are approximating till this place. So, this is the initial angular position of the satellite. Okay. So, in this problem, this is over. Now, we have to go to the part number B. So, it is telling that the situation here, this is the focus, and satellite is at the anomaly of 62.3 degree, this is 62.3. So, this is the initial position theta 0, and from there it continues till 150 degrees. So, 150 degrees, say it is going from this place to this place, this is theta 1 equal to 150 degree. So, this is given 2 theta equal to 150 degree, at which time the orbit is to be increased to a value of a by r equal to 3.6. So, here the velocity vector is tangent to the ellipse, this is the velocity vector. So, what it is asking, that now the initially a by r, this was, we have obtained it a by r to be 5/3 or something. A by r 0 we have got as 5/3, a by r was perhaps 3.33 something we have got. So, a by r 0 we got as 5/3, and from there the a by r, then a by r 0 times r 0 by r. So, this is 5/3 times r 0 by r is given to be 2. So, 10/3, which is this quantity we have got. So, from this value, this has to be increased to a by r equal to 3.6 without rotating the periapsis. So, this will be your new a 1 by r. So, this is the older one and this is new one, we will indicate by a 1 by r. So, what are the things required? So, in the trajectory transfer you will need all the velocities and other things, but from where those things will come? We have to do it from this place itself. Whatever we have worked out till now, the theory part, using that theory we have to determine what will be the velocity vector and where, in which direction it has to be given, whether the change in velocity has to be in this direction or whether the change of velocity has to be in this direction, in which direction we have to give impulse. So, that your a changes from this place to this value to this value 3.333 to 3.60. So, this is the exercise that we need to do here. Okay, so, to work out this problem, we need to find out r 1 b 1. So, this was r 0 here. Now, here this is the position, let us say this is r 1, this is the position vector r 1 and the velocity vector at this place is v 1 in this orbit. So, let r 1 v 1 be the position and velocity vectors respectively in the original orbit at theta equal to theta 1 equal to 150 degree. Okay. So, we need to find out first r 1 v 1 square divided by mu at this position, what this value will be. Okay. So, your eccentricity is known, E is known. So, and here theta is given to be 150 degree, L of the original orbit is known. So, you know that r equal to L by 1 plus E cos theta. So, from here your r 1 can be evaluated, and this will be here theta 1. So, r 1 equal to L by 1 plus E cos theta 1, and how the V 1 will be evaluated. So, for evaluating V, it's we can use this relationship V equal to mu times 2 by r minus 1 by a under root. So, in the original orbit, r position is known, will be known from this place, a will be known, is already known, mu is already known, because it is related to earth, and therefore, V can also be known. But instead of doing that, stretching this long, simply we square this. So, this becomes V square equal to mu times 2 by r minus 1 by a, and we take outside r as a common. So, this becomes 2 minus r by a. See this relationship, we have squared it. So, by squaring, this under root has been removed, and thereafter we are taking from this place r as a common. So, this becomes mu by r, and this r goes here in this place. So, this becomes 2 minus r by a, and therefore, this implies V r v square divided by mu equal to 2 minus r by a. So, here look into this equation, only r is required at the new position, a is already known, and therefore, we can work out r v square divided by mu. So, both the way we can do, it is not a problem, either you do this way or that way, it is all okay. And moreover, as we have written r equal to L by 1 plus E cos theta, this equal to L equal to a times 1 minus E square divided by 1 plus E cos theta, and therefore, r by a becomes 1 minus E square divided by 1 plus E cos theta. So, this is also r by a can be written this way. So, the same problem as I have told you, you can attempt in a number of ways, and irrespective of your ways, your result should be the same. So, therefore, V square R V square by mu becomes and you remember this equation is nothing but our energy equation. I will take up that issue again. R V square equal to 2 minus R by A, V square by mu equal to 2 minus R by A. This is nothing but your energy equation. We have written V square by 2 minus mu by R equal to minus mu by 2 A, which is nothing but your E prime, the specific energy. So, once we have rearranged it, so if we pull here R on this side, V square divided by mu, this is 2. So, we are multiplying by R by mu. So, this becomes minus 1 and here on this side minus mu 2 A, this is R by mu. Mu cancels out, this is minus R by 2 A, and therefore, R V square by mu minus 2, this becomes minus R by A, and which is nothing but R V square divided by mu equal to 2 minus R by A. So, this is the same equation, energy equation we have used. Any time you do not remember this equation, so you can derive it always from the energy equation from this particular one. Okay, using this particular equation you can always work out. Okay, so here R 1 is L by 1 plus 0.5081941 cos 150 degree, and this gives us a value of R 1 equal to 2 point, and L is also known. So, L is known to be 1.2362311 R 0 divided by cos 150 degree. So, this will become this will come with a minus sign, and therefore, this value will reduce, and this value gets reduced to 0.559891, and therefore, R 1 gets reduced to 2.2079853 R 0. So, this is the value of R 1. So, what we need here in this place, R 1 V 1 square divided by mu. So, this will be equal to 2 minus R 1 by A, and this can be written as 2 minus R 1 by R 0 if it is known from this place times R 0 by A. We can also write it like this, okay, because the A is known. So, 2 minus R 1 by R 0 and divided by A by R 0. So, A by R 0 is known, R 1 by R 0 is known. From this place, this is 2.2079853, and A by R 0 we have written as 5 by 3. So, insert that 5 by 3 here, this is 5 by 3. So, this is 2 minus 3 into 2.2079853 divided by 5, and this value will get reduced to 0.675288. So, what we have got here, R 1 V 1 square divided by mu, this equal to 0.675288. So, we have forgot to number the things. We have not numbered anywhere equation. So, you can follow as it is. Okay, so, now this is available. These are the things I am putting the things in box, so that it is easily traceable. So, whatever we have the important values, these are all placed in box. Okay, till this we have numbered, thereafter we have not done. Okay, anyway. So, 7. Okay, once we have got this value, then and what is required, that at the point, this is the point at 150 degree, theta 1 equal to 150 degree. Here the velocity is now v 1. Initially somewhere here at the initial velocity was v 0. So, how much velocity change is required, so that without changing the periapsis, your a by r, which was originally 3.333. So, from that this gets reduced to a by r equal to 3.6. This is the question. Okay, we have to get it to 3.6. Say now here, in whatever the direction we have to give the impulse. Okay. So, we will require here the flight path angle, and let us say the flight path angle here, this is phi 1. Without flight path angle, this problem cannot be worked out. Okay. So, we need to determine this value. Now, at this position, the flight path angle, if we are looking for, h equal to r cross v, and as earlier also I have told you, this can be written as r times r dot r cap or E r cap plus r times theta dot times E theta cap. And this being the same vector, this cancels out, and here you get this as r square times theta dot times E r cap cross E cap theta, and this vector will be nothing but perpendicular to the orbit which is shown here. Okay. And what this quantity is? This is nothing but r times r theta dot, and what this quantity is? R theta dot is the velocity component along this direction. So, this is r times theta dot at this position. So, simply the each vector, once we are writing as r square theta dot. So, this is nothing but your r times r theta dot equal to r times r theta dot is how much? V cos phi. Okay. So, therefore, h is remaining, because h is remaining constant, it is a constant for the orbit. So, on the right hand side we will have r 1 v 1 cos phi 1. So, whatever the velocity is here, so this we have to take. So, this equation we can utilize for finding out the value of the phi 1. This problem is bit long. Okay. It uses the simple process but it is a stretching one. Okay. And this also must be true that this should be equal to r 0 v 0 cos phi 0, which is at the initial position and this is at the final position. So, h remains constant. This is also h, this is also h, but are two different positions. So, from this place we get cos phi 1 this is equal to r 0 v 0 divided by r 1 v 1 times cos phi 0. Cos phi 0 of course is known to us. Okay, so, what will be the flight path angle in that place? This becomes known to us. Otherwise, you can use whatever the equation I have developed earlier. So, there the flight path angle equation from there it can be written very easily, but you need to remember those equations. Here without remembering anything you can do the work. Okay. In a sequential manner, if you go you will be able to do it. Okay, so, we require now r 0 v 0 here in this place. Okay, once we get this, so our job is done. So, v 0 is the quantity mu times 2 by r 0 minus 1 by a under root r 0 we are taking outside 2 minus r 0 divided by a under root 2 minus r 0 by a, r 0 by a we have written as 3 by 5. So, this is mu by r 0 under root and this is 7 by 5. So, v 0 is 7 by 5 under root times mu by r 0, mu by r 0. Of course, mu is a known quantity for the earth, so it is not a problem. So, here in this place we insert the respective values what we have calculated. R 1 we have calculated to be 2.207983 R 0. And R 0 is also given to us. R 0 is given to be 2. Okay, R 0 this is already written in terms of R 0. So, it is not a problem. R 1 we have worked out. Here we have worked out R 1. So, this we write here. So, R 0 will get cancelled out from here. This is V 1 we are remaining with V 0 cos phi 0. So, this will drop out. We are left with V 0 here, cos phi 0, V 1, this quantity is known to us, this particular part. Okay, so, V 0 and V 1. So, already V 0 we have written here in terms of this. So, you will utilize it. So, cos phi 1, this is written as V 0 cos phi 0 divided by this quantity 2.207 9853 times V 1. Okay, V 0 already we have determined, this is our V 0 here. So, we should be able to work out this problem. Okay. So, V 1 we have written as 0.5529946 mu by R 0. Okay, this we have worked out, and how we have got it? We have used this equation. As I told you, this problem is bit lengthy, and with patience if we work we will be able to do it. So, this can be written as R 1 we need to replace. So, we take here mu by R 0 as common. Okay. So, 2 R 0 divided by R 1 minus R 0 by A under root . So, this is mu by R 0 times 2 divided by R 1 by R 0 minus A by R 0, perhaps we had the value. So, we will just take the inverse of that, we will get the result. So, R 1 by R 0 already we have determined, this is the quantity we are looking for, but R 1 by R 0, this quantity already we have determined, this is 2.207 as we have written here 79853. Okay, this value we are having. So, by inserting this we get V 1 in terms of mu by R 0 times 2 divided by 2.2079853 and minus 3 by 5 R 0 by A is, and therefore, this quantity we are getting as 0.5529946 divided by mu by R 0. This is V 1, and V 0 is also known to us like the same way. V 0 we have written somewhere 7 by 5 under root mu by R 0, 7 by 5 under root mu by R 0 under root. So, everything is known here in this place. So, from here V 0 divided by V 1, this becomes 0.5529946 divided by 7 by 5 under root. Okay, mu r 0 by mu r 0, these two terms will cancel out. So, once we get this and insert here in this place, we get cos phi 1 and obviously cos phi 1 equal to, insert this value 0.552946 divided by 7 by 5 under root times cos phi 0. So, phi 0 was 20 degree. Okay. So, if we insert this value, the phi 1 and flight path angle, it never exceeds 180 degree. So, you get the correct value from here. So, phi 1 turns out to be 24.410107 degree. So, this is the flight path angle at position 1. So, at the new position. So, this is the flight path angle at theta equal to 150 degree. Numbering could have made it easy, but we have not numbered the things. R 0 by R 1 we have already determined, this is this part 2 R 0 divided by R 1, this is 1 divided by, you will have to look back and write all these values, 2.2079853 and A by R 0, this we have written as A by R 0 5 by 3. So, this value turns out to be 0.754839. So, this is A by R 1. Also, we can write A by R 1 equal to A by R 0 times R 0 by R by R 1, A by R 0 is 5 by 3, R 0 by R was given to be 2. So, this is R by R 1. So, R 1 by R then will be equal to, we are looking for this value, this is okay, 3.3333 R 1 by A. So, 3.3333 and R 1 by A is the quantity written here, A by R 1. So, we can divide it by 0.754839. So, this gets reduced to 4.4159708. So, this is R 1 by R. Now, computing R 1 times V 2 square divided by mu. What this quantity is? In the orbit at theta equal to 150 degree, this is V 1, but either you are giving impulse here in this direction or either here it may be in this direction, say this is V 2. So, we need this quantity also, what will be the in the our computation this will be required. So, R 1 V 2 square divided by mu, this quantity we have to compute, and given A 2 by R is 3.60, this is given. So, A 2 equal to, this is your R 1 position, at this position you have to change the orbit, means it may look like, if you are changing, so it may look like this without changing the periapsis. Periapsis remains same, periapsis is here in this direction, but the orbit you are changing. Maybe if you are giving here in this direction, so it will look like this. So, this is your new orbit, and for that then you have to calculate this distance divided by 2, that gives you the semi major axis. So, this is the thing being written here. So, this is A 2 by R is given to you. So, half of this measuring from the, obviously we have to this the focus remains unchanged. Okay. So, total from one end to another end, from this perigee position to apogee position, that distance is 2a, and divided by 2, that gives you a. So, say this is the half distance here. So, this half distance from here to here, that becomes A 2. So, this is given to us. Okay. So, we utilize this information. So, A 2 equal to R 1, position is not changing. So, this remains R 1, 2 minus R 1 V 2 square divided by mu, and therefore, we can rearrange it and write it as R V 2 square divided by mu equal to R 1 by A 2, and this is the quantity we are looking for. Okay. So, R 1 V 2 square divided by mu, this becomes 2 minus R 1 by A 2. So, 2 minus R 1 by R times R by A 2, this equal to 2 minus R 1 by R. So, R 1 by R, these quantities are known to us actually. So, we can directly substitute all these quantities here rather than pulling it. R by A, this is A by A 2 by R, this is given 3.6. Okay. So, this is minus sign, and first we will R 1 by R, how much this is, we look for that. R 1 by R is here 4.415. Okay. So, this value we need to insert. So, this value is 4.4159708, and A 2 by R is given to be 3.6. So, bring it in the denominator. So, this becomes 3.6, and finally, then this yields you a value, this equal to, so R 1 V 2 square divided by mu, this gets reduced to 0.77333414. So, we have here R 1 V 1 square divided by mu equal to 0.7733414. Okay. So, V 2 we can calculate, R 1 is known to us, therefore, V 2 can be calculated, this is V 2 square. Therefore, V 2 we can compute from this equation. Okay. So, computing V 2. So, either use that equation or either we can also utilize this equation mu times 2 by R 1 minus 1 by E 2. E 2 is already given here. Okay. So, therefore, I am telling this equation this can be worked out in a number of ways, there is not only one way of doing it. Computing V 2. So, V 2 is this quantity and then insert the values mu by R 1 2 minus R 1 by A 2 under root A 2 bar R is given to be there. So, this is mu by R 1 0.8793983 mu by R 1 under root. So, this is your V 2. So, velocity we have got, we need the flight path angle. So, what exactly the situation is right now? At this place the V 1 was known, the flight path angle this phi 1 was known. Okay. Now, the V 2 is also known. At this point, say the V 2 may be here in this direction, if this is the V 2 direction. Now, we have to calculate the flight path angle. So, flight path angle will be calculated from this horizontal. So, this is your local horizontal which is perpendicular to this. So, then this becomes your, this angle will be phi 2 and this angle is your phi 1. Okay, seeing the situation, I will draw again. So, this is the line here and V 1 is in this direction, the local horizontal is like this, it makes 90 degree with this place. Okay. And therefore, this is your phi 1, the flight path angle, the other angle V 2 may be here in this direction. So, the corresponding angle this is phi 2. So, V 2 is known to us, we have to determine this phi 2 also, and if we get this, then we will be able to know what is the separation between these two vectors. Say this is the V 1 vector and this is the V 2 vector. Okay. So, what will be the change? This is delta V. How we will know? If this we know the difference between V 1 and V 2 vector, which will come in terms of delta phi. So, this delta V can be calculated using the parallelogram rule. Okay, so, next step in this is to find out now find phi 2. This is the objective, this is equal to what? If we get this, our job will be done, but still we are away from the final result. at the position new position here in this place, this is r 1. Okay. And once we are looking for the new orbit, that the new orbit may it may look like your new orbit may look like this. So, for this new orbit you have a 2 value which is different. Okay. So, for this new orbit we are writing this L 2, because once your A is changing to A 2, or we have used here A 2 value here, we have used here A 2 for the new semi major axis. So, corresponding to this is L 2. So, this equation we write as 1 plus E 2 cos theta. So, 1 plus E 2 now cos theta equal to 150 degree. So, this is L 2 by R 1, this becomes equal to 1 minus 0.866024 E 2. This is R 1. So, R 1 times 1 minus 0.866024 E 2, and therefore, from here we get this as. So, we have to solve. Okay. So, A 2 by R 1, this quantity is A 2 by R times R by R 1. So, inserting these values, A 2 by R is given to be 3.60, and then we will have R 1 by R value, this is known to us. So, this is 3.6 and we have already calculated, this was 4.4159708. So, this turns out to be 0.8152227, and once we use this A 2 by R here in this place, if you use this here, okay. So, you will have A 2 0.8152227 times 1 minus E 2 square, this equal to 1 minus 0.8660254 E 2, and you know this is the quadratic equation. Okay. So, if you solve it, this comes into this format, E square minus 1.062317 E 2 plus 0.2266586 Okay. So, the solution of the E 2 is then 0.2956358, because it is a quadratic equation. So, the solution to this comes, we will have two values for this, another one comes out to be 0.76 66816. So, these are the two values of E 2 which comes from this equation. Now, which one is correct and which one we should use and which one we should not use? This is the situation condition right now. Okay. So, E 2 is known to you, E 2 is known, E 2 by R, this is given to be 3.60. Okay. So, let us explore what will be the periapsis position R p. So, R p equal to A times 1 minus E, this equation we can utilize. So, here A here in this case is 3.60 times R, and if we use this value or that value. So, depending on here you can see that what will be the periapsis value. So, we need to compute this. Okay. So, if we put here 1 minus 0.7666816. Okay. So, let us say this I approximate this as 0.75, okay, for convenience. This has nothing to do with our computation. So, 0.360 r times this becomes 0.25 means 3.60 divided by 4 r means this becomes 0.9 r. That means the periapsis is less than the radius of the earth. So, this simply implies that if you are taking the solution, this solution, okay, 0.766 for the eccentricity. So, in that case your periapsis, it goes inside the earth, means the orbit becomes something like this. So, this is not a possible orbit, because it is striking the surface of the earth. If the satellite goes in this path, so it will simply go and hit the surface of the earth and it will get destroyed. So, this is not a possibility. Therefore, E 2 equal to 0.766, 0.766, this one is rejected. We do not work with this. So, what is our option? E 2 equal to 2.295, 0.295, 6358, 6358. This is the possibility and we will work with this. So, this is our E 2. So, corresponding L 2 then becomes, we know this quantity will be r by, we know that r equal to L by 1 plus E cos theta. So, here if we write r 1 is not changing, r is not changing at the position where we are giving the impulse, which is here this point. Okay. So, we keep this as r 1, while L will change to L 2 and 1 E 2 E will become E 2 and cos theta equal to 150 degree and plus, and therefore, this implies L 2 equal to r 1 times 1 plus E 2 cos 150 degree, and which will turn out to be, if we use this value. So, this will turn out to be r 1 times 1 minus 0.8660254 E 2, insert the value of the E 2 from this place. So, this gets as r 1 times 0.7439718. So, this is your L 2. Now, we are close to our work end, but still it will take some 10-15 minutes and we will wind up this. So, H V 2 r 1 cos phi 2 and H will write as H 2, because once you are giving impulse, so the orbit will change, it will not remain the same orbit. Therefore, cos phi 2 from this place, as earlier we have used the equation, the same equation we are using here, only thing with the variables change here, H instead of H we are writing here H 2. Okay. So, at the new position, this is the this r cross v, the specific angular momentum which we have called, and this is the v 2 position, the velocity at the position r 1, this is r 1 itself, and this is the corresponding flight path angle. So, cos phi 2 then becomes H 2 is nothing but mu times L 2 under root, okay. H is equal to mu times L, H square equal to mu times L. So, from there we are putting it V 2 R 1. So, all these quantities already we have calculated. So, once we insert those values, we will get the solution. L 2 by R 1 under root So, we will write it like this and insert the values. L 2 by R 1 is 0.74399718 under root divided by this quantity, this will be R 1 V 2 square divided by mu under root. So, this quantity is also known to us. So, we just insert in those values 74399718 under root divided by 0.7733414. So, this turns out to be 0.98082774. So, this is cos phi 2. Okay. So, R 1 V 2 square divided by mu, and see from here we can write this phi 2 value. Phi 2 will turn out to be 11.23761 degree. This is phi 2 flight path angle, and this quantity you will similarly you can write as this is 77. Already we have used it here. So, this is 77.33414. So, now this flight path angle is available to us. So, coming to the final version. So, this is R 1 here, okay. This is the local horizontal, and V 1 is here in this direction and V 2 is here in this direction. So, V 1 angle, this angle from this place to this place, this is around 24 something we have calculated. This is 24.410107 we calculated. This is phi 1, and the angle this one right now we have calculated, this is phi 2. So, phi 2 is turning out to be phi 2 equal to 11.237612. So, this is your delta phi. Okay. So, if your one vector is here, another vector is here, this is your V 1 and this is your V 2. So, you need to give this delta V impulse, while this is delta phi is given here. So, these two vectors are available to us. Magnitude wise it is available, and we just need to compute this delta V. So, delta V is the impulse magnitude just we require. So, delta V will be equal to V 1 square plus V 2 square minus 2 V 1. You can look from the this triangle here using parallelogram rule, you can construct it. Okay. This will come again in the trajectory transfer, because the most of the things we are from the orbit part. So, I have done this problem here. So, delta V you put the values here 0.8217107 square, this will be mu by R 1 plus 0.879393 square divided by mu by R 1. These are the corresponding values we are inserting, minus 2 times R 1 R 2 this V 1 V 2 value we have to insert here. So, 0.8217107 times 0.8793983 and times cos delta beta. So, cos delta beta is 24.410107 minus 11.237621. So, you compute this value, this is all under root sign. So, this will turn out to be delta V equal to okay, and thereafter mu 1 and mu by r 1 and mu by r 1 is associated with this. So, this I also we should write here, this is mu by r 1 times. Okay. So, mu by r 1 we can take it outside and this should be a square here actually. So, mu by r 1 this is square after coming. So, therefore, we will put here one under root sign to this is under root because it is a coming because of a square. Okay, look back all these values as I am concluding it. So, this will turn out to be 0.2033 mu by r 1 under root. So, this value is known to us. So, therefore, delta v. So, how much impulse is required, in which direction the impulse is required, this we have computed from this place. Okay. So, as a final final observation. So, this is your abscess line, somewhere the focus is located here. This was the original orbit and 150 degree lying somewhere here. So, this is theta 1 equal to 150 degree. Okay. At this point the V 0 is like this and this is the local horizontal. So, this angle is phi 1 equal to 24 point something here and the new velocity vector is somewhere here. This is the original, I am not showing the magnitude wise. So, this is V 1 and this is V 2. So, the new angle is from this place to this place. So, this angle is 11 point something. Okay. So, this is your delta phi. So, in which direction you have to give impulse? If this is one vector, okay, and this is another vector, okay, and whatever the magnitude is there. So, accordingly depending on the this delta phi value, you will know in which direction you have to give this impulse and this is delta v is available to us. So, this is the situation. So, with this new thing your orbit will change and orbit will look like this. So, overall, so your A changes without change of the axis. So, the center of attraction remains same, but the total from this place to this place, this distance becomes your 2 A 2 and half of this will be the semi major axis. Okay. So, so, I feel this is enough for today. So, we have done one major problem here which requires a number of skills and integrating together different situations and solving the problem. So, we conclude here. So, thank you very much.